In this module, we're going to describe an approach called variance stabilizing normalization, or VSN. So VSN is based on the model that we described earlier in the background adjustment modules. And the basic idea is to write down a model that describes the behavior of gene expression or whatever quantity we're measuring across replicated arrays. So in this notation, we have Y being the observed intensity, I representing sample, replicated sample, and J representing gene. So where is the need for normalization represented in this formula? Well, we have two places. One is the beta background levels, which can change from sample to sample. And we also have this gain, AI, that can change from sample to sample. In VSN, we consider this the additive part of the model, and we consider this the multiplicative part of the model. And it's something that is motivated by real data. This appears to be how real data behaves. So in the model, we have some a background level, an additive measurement error, the true expression level for gene J, the gain that changes from array to array, and then some measurement error that's multiplicative. So if we generate data from this model with a simulation, we get data like this. And you can see the nonlinear effects that we've been observing in many of these examples. So if we use beta 1, 24, beta 2, 20, that's two arrays with two different background levels, and then we also have two different A's, different gains. We see a shape like the ones that we've been seeing. At the low level towards the left, where the theta is close to 0 and there's no signal, we basically see the log ratio of the background levels, right, which in this case is about 0.25. Over here, we have the background level having little effect, and this level, which is not 0, is basically driven by the difference in A2 and A1. So the model can easily generate data that looks a lot like what we see in reality. Now, if we know the background level and the gain, if we're able to estimate that, we can then normalize the data. We subtract the background, divide by the gain, and we get pretty close to the theta value that we're after. There's a problem. There's still a problem. If we do this, because of the multiplicative effect, we make an MA plot comparing the intensities from sample 1 to the intensities from sample 2. We can see that the variance grows with the mean. It's very clear. And that's something that we have seen before, and it's one of the reasons why we take the log. Now, VSN is an alternative to taking the log. Why do you want an alternative? Because, as we have seen before, if you take the log of a quantity like this, then you get an explosion of variance for the low values, as predicted by the simulation based on the VSN model. So we have an increased variance in the raw scale, increasing with mean value, and an increase in variance for low mean values if you take the log. So what the variance stabilizing normalization approach tries to do is find a transformation of the data that's not the log that will have constant variance. It will be stabilized across the mean values. So here's the mathematics behind it. If we have a random variable y, when on average it's mu, and the variance is a function of mu, we have a case where the variance changes with the mean, and for many of the downstream analysis we do, we don't like to have that. We like to have a variance that's independent of the mean. An example of this would be the Poisson, for example, where the variance increases with the mean, and the microarray data we see in practice, which has variance that increases with the mean. So if you happen to know the function that describes the dependence of the variance of the mean, if you happen to know that, then you can find a transformation f, and it's actually just a matter of taking the integral of 1 over the square root of that function. Then once you find that function, if you apply it to the data and you take the variance, then this quantity here, the transformed data, no longer depends on the mean level. And we have a variance stabilizing transformation. So in VSN, this approach is applied to the microarrays where you have this additive component and this multiplicative component. And if you do the math for that case, for that model, we end up with the hyperbolic arc sine of the data minus the estimated background level divided by the gain. Now, unlike the log, when we take the log of this quantity, we're going to run into trouble because this number can be negative. With the hyperbolic arc sine, that's not the case. That function is actually similar to the log, especially for large values of y, these two converge. But for low values, it actually is quite different. And it has an advantage that it doesn't fan out as you approximate 0, as y approximates 0. Does it work in practice? Here's that data that we've been looking at in the previous modules. You can see the curvature. VSN will describe that curvature as a background level that's around here, a difference in background level. And then the difference that you see down here, although that's closer to 0, as a difference in the gains. It tries to estimate those values, and it uses an approach similar to all the others. It assumes that most genes don't change. And if you can assume most genes don't change, that gives you a way to estimate the beta and the A. So you can do that for several genes, and after you apply the VSN transformation, you get data like this. It's very similar to the previous two approaches, to quantile normalization and low-S normalization. So approaches like VSN are being applied to RNA-seq data. We're going to learn about that in later modules.